Okay. All right, we're good.
Testing. Hello. Hi. Welcome back to Vector Semantics today. So, we are well along in the process of understanding how computational cognitive models have emerged into the world. Now let's talk about some of the building blocks. Vector semantics is one of these things that it's a little bit of a far out concept when you're not used to talking about language in a programmatic way. Let's go. So, also this is a image drawn by a robot, of course, as all these start with now. Okay, so here's the core premise. And this is a pretty huge problem I say problem like a scientific problem, things that are trying to be tackled over time, and philosophical. But how does a symbol become a thought? How does something that is just like an abstraction become something that we actually use for language and knowledge and words and such? Let's start with a simple example. I give you the letter C. This is a symbol on its own, but we tend to combine this fundamental symbol with other similar fundamental symbols, right? As is demonstrated in the rest of the words above the letter C right here. If I give you CA, well, you might start to have a faint understanding of some kind of idea associated with it, but it's not a complete symbol. You might not be getting all the way to cat until I give you the T, right? Somehow, these three symbolic chunks of angles, just weird lines and shapes, have evoked in your mind the concept of a cat. That might touch on all the different parts of your knowledge around cats. It might touch on your experience of cats. It might touch on the features of cats, things that are relevant to cats and related to cats. But overall, the symbol CAT gives you the ability to wield the concept of cat. It evokes in your mind the semantics of what a cat is. Now, what if we go back and we do the same process? I give you a C, I give you an A, and I give you an R. Oh, shoot. Wildly different semantic experience, right? You are getting a vehicle that's made out of inorganic materials, and it moves, but it's totally very little to do with the concept of a cat. There's some mild amount of overlap. They're both part of human systems, and humans tend to have cars and have cats in their vicinity. But this is a pretty interesting little jolt, because those symbols are very close together, right? CAT versus CAR. The difference would be between the lines and shapes of the R and the T, and yet they are wildly different semantically. So this is the phenomenon that we're talking about today, is semantics. This is the thing that we are great at, right? The whole point of language and words is that symbols mean things, right? Otherwise, this presentation, the written or spoken, there's no point to it. If none of this could mean anything, and it was just abstract symbols flapping about in the wind, what's the point, right? So, pretty core understanding of semantics are real. They are things that we do. But the standing question, and this is one of many that, as always, none of them are solved, but a standing question of what the heck is the process, right? Let's walk through this. A pattern of light in a particular shape hits your eyes, right? Or vibrations hit your ears, right? But either way, they take these specific shapes. Me saying the letters CAT, or rather, let's go with saying the word cat, right? And you reading the letters CAT, these are two different shapes that exist in the world as symbols, and they signify something to do with the animal type. So those patterns get into your cognitive system through your receptor neurons. Go take a neurobio course if you want to learn more about that. It's pretty wild. but the idea is something on the surface changes, something in your retina changes, something in your inner ear changes, and it's able to convert that into neurological signals. So now those signals are in brain space. They are in a neurological pattern, right? They are transmitting neurologically. Electrically. No. Electricity is involved. Or rather, electric potentiations. It's a subtle distinction there. So, the words are now inside the brain, somehow. But at some point during this transformation, right, the information goes in and starts to transform, the two symbols CAT and CAR diverge, right? They don't end up activating things that are close together. They end up activating things that are actually quite disparate, very different things. And I was going to write a joke about a cat, but I was tired. Let's skip it. Cats and cars. The specifics of this process of how symbols in the world evoke meaning in the mind, it's elusive, right? This is not an easy problem. The full networks of brain regions activated by even a single word are not easily captured in scientific models yet. You know, we are obviously always chipping away at these questions. Modern neuroscience does many things in this vein. But, you know, that doesn't mean that we have to stop and not try to model it, given our first impression in you know, wind back 10, 20 years. So, how do we actually capture something like this in a computational modeling scenario, right? At minimum, this is a useful thing to have in your mind. Neural systems necessarily deal in informational activity, right? So informational activity can be captured with mathematical computations to some extent, right? You can see the perceptrons unit for more. Therefore, if neurons can do it, then we can at least capture some of that phenomenon mathematically. Math is a good mapping onto basic, like, information theory concepts, right? Now, what's the point of me stating this? Well, that's just to set the background of, if neurons can do it, we can probably figure out some way to represent what's going on in those neurological patterns. But then let's continue. So if we can capture these things in math, what's the point? What does that actually give us? Why is math better suited to understanding semantics? Well, for one thing, I forgot a line here. First of all, what do you do with just symbols? Oh my god. Hang on. This freaking thing has ads in it. Oh my. I might need to pause. Okay. We might need to edit a little bit of this out. Let me rewind a little bit and see what I can do. So, let's see. Where was I? Okay, so why are we going to convert words into math, though? Well, for one thing, before we get to the things on the slide, this is computational modeling, right? Of course we're going to get mathy with it. But another thing is that what, in your mind, noodle this, what could you actually do with just arbitrary symbols, right? The letter CAT doesn't have any inherent value or meaning. It's not connected to anything. Because think of it like this. I could say, we could have called cat anything. We could have called cat Cam, right? When we were coming up with letters and words that assigned to things, we just kind of arbitrarily pick symbols. But math enforces certain relationships, relational questions, right? So one big one in the semantic space is, well, how close are these two things? How closely related are these two things? So, for example, cat and car, we know, aren't really closely related at all. They might be closely related symbolically in that you only have to change one letter to alter it. But semantically, they are far disparate, right? So, but then cat and dog, which don't share a lot in terms of their shape, they're much more closely related conceptually. They're both mammals, they're both pets that humans have, they're both, modern, we've certainly changed them from their wild species, right? So this concept of closeness is a casual measure of distance, right? So when we talk about semantic relatedness, we can use the word close and we kind of understand these things are close in meaning. The word jump is very close to the word leap, right? They're not quite exactly the same. Flame, fire, burning, right? They have things in common, and you know that they're closer together than flame, fire, burning, and I don't know, the concept of justice. Right? These are very different parts of the semantic space. And while we can't totally pin that down mathematically just yet, we can start to, right? So we can get the concepts into a workable mathematical space. But the question still remains, how, right? How could words become math? What does it mean for that to happen? Didn't finish a line there. Let's take an aside into something that more clearly illustrates this concept. Colors. Colors as numbers, colors as meaning. We humans love colors. They are a huge part of our perception of the world. And sorry for anyone who is colorblind. It is a thing that you cope with, but it's also, I assume you have a great understanding of how important colors are to navigating the world. So, yeah, it's a little bit easier to talk about this interesting binding question of how can a mathematical representation map well to meaning? Well, let's chase this through color. You can represent color in a variety of ways. One simple one that we use a lot is color as a single number, which is the wavelength, right? If you know a little bit about physics, or you've ever seen this kind of stuff, this light-based analysis of colors, you know that the wavelength of the light that's firing at your eyeballs is what will determine, is how we parse it into color, right? Higher end, or I guess longer wavelengths, so lower frequency, get into red and infrared, while as in the short wavelengths and the higher frequency get into violet and ultraviolet, and then all the colors exist in between on the line. A single number can represent color. Interesting. But that's not it, right? There is more to color than just the hue. You can also get into saturation, for example. So we can extend that color line down into another dimension. We have two numbers now. We have a vector of two numbers, hue and saturation. Hue determines that frequency and wavelength, and saturation determines the how much of that color is present, right? This two-dimensional space, can you see my mouse? Yeah, you can. This two-dimensional space captures a lot of information about colors. Continuing forward, you can add a third dimension, and also several others, but we'll just focus on three. This is a classic thing. If you've ever done any web development stuff or programming where you're working with color, you know that we break color on a computer monitor into three parts: the red, the green, and the blue component. How much of each of these is present? Black will be down here, where none of the colors are present. White will be up here, where all three colors are maximized. And then all the rest of the colors happen in between. Over here is fuchsia, magenta-ish. Here is just red, 25500. Over here is just green. We don't really see the blue part because it's sort of at the back of the cube, but you could imagine down here, at this vertex would just be... Wait, is that right? Yeah, that should be. I think they've... Erroneous. This is what you get for snagging stuff from Google. So we can see, though, that the colors can be represented in a three-dimensional space. That we've gone from one vector to three different a one-dimensional vector, a single value, to a three-dimensional vector, multiple values, to capture the concept of color in the reduced mathematical form. Okay, who cares? Well, even though color can be abstracted into these simple representations, humans love giving them names. We have no trouble at all assigning names to colors. Now, the naming conventions aren't necessarily consistent over time, but you know, some colors lack words for certain, or some cultures lack certain color words, while others might have tons of words for what we might just all call blue, right? But the fact is, we can divide up this region, this mathematical two-dimensional region here on this XKCD chart. XKCD is a comic, in case you're not aware, webcomic. But so this whole region we might call green. Now you might start to argue and bicker over the corner here. It's like, is that still green, or are we getting to yellow? Is it kind of a brown or olive? I don't know. That's up for debate. But this is based on a surveying and drawing lines based on what people report, right? So these are regions of the color space that we assign conceptual values, right? And we come up with these all the time. We love to make color values. From there, it's a little bit easier to jump to ascribing meaning to a color value. We love to do this. It's a little bit arbitrary, but it's based on something, and we'll talk about that. For instance, we often think of like red is associated with love and passion, or sometimes speed if it's on a car, or blood. Red has all these connotations based on where we've seen it before. Interesting concept. Green is to do with nature and growth and health, and somehow we've bastardized it into money as well. But these concepts, these ideas, these semantic connections to color, you know, again, it's subjective. Despite Pop Psych article, don't paint prisoners' rooms pink. Who cares? Like, it doesn't work quite the way they say it does. It's not non-existent, but it's not universal. Point is, we do still ascribe some meaning to colors, right? How does that happen? And I can give you the very simplified version. It's repeated occurrence in meaningful contexts, right? Green is natural in our minds because it's highly represented in natural environments. When we go to nature, we see lots of green, right? Red might acquire this passion concept because of its correlations, right? Blood is red. We associate the heart with love and passion, that kind of stuff. Here's the question, though. Would we think white is sort of pure if paper was always gray, blank paper was always gray, if wedding dresses were all deep scarlet, and if, you know, most powdered materials came back to like a dark black instead of a bright white? Like salt. Think about salt. If salt was pure salt, if it was just flat, matte black, would we think about purity as connected with that color? It's a strong question. We don't live in that reality, so we can't tell. But this is the idea. So we are able to take this thing, which is very well represented by a simple numerical vector, and put it into a space where we can ascribe certain meanings to it. So, can explore that again. Color math to meaning vibes, right? So now we're starting to see how these bindings can occur. Not that they're perfect, not that they're all like rigidly well defined, but that we can trace the possibility, right? And this is sort of how this approach to modeling semantics begins. So colors are easily represented by math, and they can be tied to semantics through co-occurrence, right? So FFOOOO, right? You might see this on a website, right? Our favorite old notation, hexadecimal notation for colors. FF means 255, 00 means 0, 00 means 0. What's that mean? Maximum amount of red, no green, no blue. That turns into the concept of like the word, the meaning, the label, the name red, and red can be associated with love and blood and hearts and fire and heat and blah. That concept, that kind of pipeline for mapping between a numerical space and conceptual activations in our minds is very useful going forward. So let's try to talk about semantic vectors. Words as semantic vectors. So we're back to words. Words are rich with meaning. We use them all the time. They're all over this screen, right? You know many things about words. Because that's the whole point of words. They are designed to signify things that have meaning. In colors, we saw up to a 3D representation, but you can go a lot further than that. In fact, vectorized representations could be as large as you want. We'll talk about some examples here. And the more values you have in a vector, the more potential relationships you can capture, right? It's not just red, green, and blue. It's any number of connections between other concepts, right? So since semantics are at least partially driven by this co-occurrence idea, we can start finding ways to represent words as numerical values in larger vectors by looking at how do they occur together in natural text, right? We have huge amounts of natural text that humans have created. The question is, can we draw a useful semantic model of what those words mean in relation to each other from how they co-occur? Another way to think about that mapping is a dictionary is entirely words, right? The whole point of the dictionary is a word can be a referent to other words, right? Now, you wouldn't just build, you could build a semantic representation, a semantic vector representation out of a dictionary, but the point is that these things kind of map together, they fold together. It's the idea of how do words relate to other words? It's kind of our natural state of interacting with words. It's kind of weird, but here we are. Here we can have a quick look at some of the vector space here. Pizza is very closely related to pizzas. Sandwich is close to pizza, right? It's all like foodstuffs, right? They're kind of far away from train, and they're very far away from Twitter, right? Salmon and fish over here is still up here in this sort of like almost foodie area. Here's a bunch of transit. You know, down here we have things that are related to car, things related to train, fish, pizza, Facebook, Moscow, London, Paris, right? Now, a quick note. Remember, these actual vectors, when we're working with them in vector semantic world, they're huge. It's like 1,500, 100,000. These vectors are large numerical vectors. What we do to show them in these kinds of situations is we flatten them out, right? Kind of like you are flattened out into a shadow when the sun, casts down on you. You don't get the whole picture, but you get the outline, right? And here we're seeing the semantic shadow of some of these ideas and where they fall, right? So knowing that pizza is much closer to pizzas than pizza is close to tweet, it makes a certain sense, right? Now, how you do that is a whole other kettle of fish. Let's continue though. So, a simple co-occurrence vector. Walk with me through this. I didn't do the animations. We'll just talk about it. How might you compute a vector? Remember, that's what we're talking about. Multi-dimensional numerical thing for a single word. So for the word cat, we could take some huge data set. For example, Wikipedia is a fine data set. And we can set up a vector where each value is the number of times some other word co-occurs with it, right? And what do we mean by co-occur? Well, that's kind of up to us to define. In this very, very simple co-occurrence matrix we're going to do here, it would be per sentence, right? We could say per document. That's a little broad. We could say only if they're right next to each other. That's a little tight. So you can make it maybe more in this per sentence or per paragraph idea. But the idea is, for each sentence of Wikipedia, the whole dang thing, you would run through and you'd say, okay, if the word cat appears in the sentence, then for our cat vector, each other word in the sentence, we're going to increment its position in the vector, right? The vector is as long as the number of words in Wikipedia, number of kinds of words in Wikipedia, right? The word a shows up all over Wikipedia. How often does it co-occur in a sentence with cat? Here I've arbitrarily selected 9 times, right? of only 5 for whatever. Meow, though, that's occurring with cat quite a lot. Maybe not literally in Wikipedia, but meow, right? That's going to have a high representation, co-representation, co-occurrence representation with cat, right? Dog will probably also have a fairly high amount. I don't know, I made some of these up. They aren't all very illustrative. At the end of this process, though, so you're going through Wikipedia, you do this for each sentence and each word in that sentence. You run through, you write your little Python script, run through, blah, 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 eat the whole thing. At the end of it, you would have a vector of how often every word in Wikipedia co-occurs in a sentence with the word cat. Okay. It's a bit brute force, and it'll be very two things. Sparse, since most words don't co-occur with cat. For example, the word bullet train, hyphenated, probably not going to show up with cat very often, right? So it would have a 0. A lot of words are going to have zeros with this in this vector, right? It's also huge. The whole number of vector values in this vector that we've just computed for the word cat out of Wikipedia is going to be about 170,000 words, 170,000 values, because that's about the size of the English language. We can kind of assume almost every word's going to show up in Wikipedia. So, this is a huge vector, but you know what it does? It gives us a mathematical representation of what is cat most connected to. And I would say that it being very well connected to the word meow, that is kind of the shape we want in this vector, hey? The co-occurrence of cat and meow is a meaningful connection, and therefore it's good that this approach would have it better represented in the vector space. So let's take a sec to sort of peel apart, what is this actually buying us? Why is this good? So if we compute cat and we compute dog, we can see how close they are in this flattened 2D space, right? And, you know, maybe they are farther away from car, maybe they're far from other things. We can also do this other interesting thing where if we do the same thing for wolf and tiger now, we can see the difference between dog and wolf is actually similar between cat and tiger. So this concept, this domestic to wild distance, is computable, and it might end up being stable. It's this extra level of abstraction. You'd have to test these things, of course, and using our stupid brute force method, it's not going to be holding up. But this is the kind of stuff you have access to when you get into mathematical space. It's not just how far apart, it's not just how far apart is cat and dog, it's are the distances between related terms similar across other pairs of terms. It's a level of abstraction. It's a level of domestic to wild abstraction, among many others. We'll see a couple more. So, this is the concept of vectors from words. We start to see this at how these mathematical vectors of words can be useful, right? It's not just in terms of representing the semantics, you know, mathematically, but also transforming them. We can translate, we can apply the same transformations to many of these vectors and get things that are relevantly connected. So for example, you can apply a past tense vector that might change walking to walked or swimming to swam. You can apply a capital of vector to get from a country to its capital city, right? Canada to Ottawa, Spain to Madrid. So while the individual word vectors are useful as a sort of like basis, just like red, green, blue are in colors, you can compute a single semantic vector from an entire set of words. So this is actually a super useful conceit. You don't have to have, if I'm trying to work with a bunch of words at once, say I'm sending a query to Google or Amazon or something, that query can be converted into one vector, which will have lots of lumps. It won't just have a lump with cat at meow. It might have, if cat is in a sentence, then meow will go up. And then if it has like sounds animals make, meow will go up even further, right? So our vector will just be a pile of all these conceptual words moving together. So this is super useful. You could convert an entire document to a single vector. You could convert an entire AI prompt to a single vector. You could convert a Google query, YouTube video descriptions. I mean, this is all how recommenders work, right? It'll take this thing that you spent time on looking at Amazon, and it'll convert all of its text into a vector, and then it'll look for all the nearby vectors and say, oh, you might like this. You might like this. This is how Amazon was told to do that thing a while back, about 10 years back. It was showing that it was predicting when women were pregnant before they knew it, just based on the kinds of things they had been shopping for. Freaky, but real. Okay, so this is the concept. How we get words and whole sentences, whole documents, whole queries, whole strings into numerical mathematical forms. So this is from a previous lecture of mine. It had some nice animations. Instead, we'll just carefully walk through it. Consider 3 documents in this space. Document 1 is a dictionary of mammals, right? So let's find document 1 in the vectors. Document 1 has like nice equal representation of all 3 of dog, capybara, and cat, right? It's nice in the middle, down the middle, right? Because it's just a thing about mammals with equal representation. A pet guide might be document 2, which might talk a whole bunch about cats and dogs, but almost nothing about a capybara, right? If you don't know a capybara, look them up. They're cute. Here, we'll do a quick. This guy. They like to sit under water fountains. They're the chillest rodent in the world. Anyway, back to our representations. Okay. So, and then finally we have document 3, which is Capybara's Monthly. Which, obviously, not going to talk a whole lot about dogs. Might maybe mention cats, but otherwise it's almost entirely about capybaras. Now, we're faced with 2 queries, right? Query 1, cats but also capybaras. This is us asking Google, for example. Cats but also capybaras. It has 2 words decently equally represented, right? And so it'll kind of fall into this space with a little bit of representation with cats and a little bit with capybaras. The nearest vector to this one is almost certainly the Dictionary of Mammals, right? Because Dictionary of Mammals is going to equally represent all these different mammals. That would be the first thing to pop up if you said cats but also capybaras, ignoring the but also, because those are super irrelevant. Query 2, though, has cats, but more importantly, capybaras, capybaras, capybaras. I am crazy for capybaras. You have hypersaturated this query, and thus its vector, its numerical vector, with values from the capybara vector. Meaning, this second query, this longer one, if in case that was not clear, is definitely going to turn up Capybara's Monthly, right? It's going to pull the thing that is closest to it. The angle between these, the similarity between these vectors is much closer because this one is enriched with lots of capybara discussion, whereas this one was a more even-keeled type thing, so it's probably going to pull up Dictionary of Mammals. This is part of how Google works, right? How it does the rankings. It does also a different kind of search. Go take Information Science 220 for that. So, that's the idea. These vectors end up being a useful representation for computing things like semantic differences, semantic relatedness, semantic transformations, right? Capturing all these things. But the version we showed today is useless. No one uses it. It would be huge and sparse and bad. So this co-occurrence vector idea is just to illustrate the concept, right? Because it's too simple. So first of all, it's huge and sparse. You would want to compress it. For example, GPT's vector lengths are down to about 1,500 values versus the 170,000 values you would need to do the exact complete, English language. Now, they do this through a lot of other kinds of processing that we won't get into right here, but the idea is you can capture rich semantic values in fewer dimensions than you need the entire English language. Other things that connect to this, word to vec is a processing. Here's actually a paper on it. Efficient estimation of word representations in vector space. It's a more general approach. The way it handles this whole thing, one of the insights it offers is this sort of continuous window. It doesn't just arbitrarily pick, hey, sentences matter the most. It has a moving window to make sure words are represented, connected to things all across the space, right? A little more cleanly, right? BERT is another version of this sort of vectorization that adds in the idea of adaptive vectors. So before BERT, the numerical vector would be pre-computed for the language. It would have one solution. But now the vector is adding in additional things like, well, what all is in the context of the sentence? It's not just saying, here's the sentence, let me slam all of these vectors together, and now you have your sentence vector. It's saying, well, the words in this sentence will determine which parts of the vector are more important to emphasize, right? And continuing even further, transformer architecture models add the concept of attention. So this allows the model to weight different words and values in the actual prompt in the text based on their relevance, which is again another layer of computing that's not, it's not just the base value of words, but it's a layer of computing here. So but just to give you the idea, it might hyper-emphasize important words in a sentence, like Sally sells seashells by the seashore. Seashore, huh? Seashells is a pretty important word in that sentence. It should probably be a little extra emphasized, because what is she selling? Well, that's part of the whole, that's a pretty key idea here. Now, her name might also be extra emphasized, but seashells seems to be a very strong topic in this sentence, right? Also things like syntax. So knowing that Joe threw the ball at Sally. The system doesn't just say, Sally's right next to at. Sally and at are very important. It's a little bit more nuanced than that. The attention mechanism is able to show, okay, wait, at Sally is an object here. I've forgotten. I've never been great at the syntax. Either the direct object or something similar, right? Sally is having something happen to her. Let's go find out what it was. So by looking at the right spots in the sentence based on, grammar rules, it's able to learn those grammar rules by having the attention system set up this way, right? So, and there's tons of other language abstractions available at this layer. Attention really was one of the key things. There's a whole paper on that. I might throw it in here. Lots of other things, similar language abstractions, right? And once again, starting to get kind of freaky that things have progressed to the point where models are pretty dang well aware of who threw the ball at who when you just emit the sentence, Joe threw the ball at Sally. Woo. So, where are we at? And what's next? So this kind of semantic vector stuff, it has progressed quite a lot, right? Modern AI is built on this, though. The idea that a word or a bunch of words can be converted into a numerical representation makes them more available for neural networks to chunk them into inputs and process them through all of their, many layers and do their weird abstractions. It's a little bit more pre-digested, right, than trying to do it based on raw symbols, raw characters and such. And this is how modern AI does it, right? It doesn't just interact with the symbols themselves, but in terms of their semantics, right? It can figure out your typos when you're interacting with it because it's able to situate your prompt in this robust, adaptable, focused portion of semantic space. It doesn't care that you misspelled banana. It gets it because it doesn't need perfect syntax and perfect symbolic structure like a programming language. It converts it all into this continuous hyperspace, right? This is how it can get what you mean, not just what you say. Yeah? So, back to one of our core topics of the course, though. Is this how brains do it? Probably not. Not really. Humans certainly have a bit more advanced comprehension skills than just building on co-occurrence, right? For example, just because knife co-occurs with murder a lot doesn't mean we can't, like, separate the concept of knives are murder weapons when we're cooking. We don't run screaming out of our kitchens just because there's knives in it, right? I'm not saying that would be the logical response, but we have more layers of monitoring processes going on. We don't have to just be like, oh, those things are related. Whoops, gotta get out of here. In fact, a lot of pretty regressive thinking comes from just thinking in terms of co-occurrence. But, the fact remains that we can abstract some of what our neurological systems are doing in an informational way to a mathematical representation. And also these models are continuing to evolve, right? The adaptive context by Bert chips away at some of that context sensitivity question right there. And the attention mechanism adds this fairly critical layer of a human cognitive capability to this whole, converting words into math thing. Now, does its attention truly resemble humans? Probably not, again, right? That's not always the goal with these things, but it does sort of abduct some concepts from human neurological and cognitive processing into its system. Now, whether, it's a start, if nothing else. So, in the same realm, though, there is some research showing that humans tend to do a sort of foraging behavior when they're navigating memory, when they're trying to remember related concepts and try to remember something that it learned recently. I say it, that we learn as humans. And one recent example, I'll skip to this first and we'll talk about Pymantle. Neural evidence of switch processing during semantic and phonetic foraging in human memory. This concept of being able to move about a space internally. Interesting. Sounds a little bit like vectors. There's a different way of representing that kind of space neurologically, but the whole idea is this concept of putting this into a math space, situating it into a space, is not without merit, right? We may not do it the exact same way that the space, that the word to vec does it, but it's not alien from the concept of how we might relate concepts mentally, right? And a game that is fun for this is Pymantle. Your goal, it's kind of like Wordle, right? But it's not lexical, it's semantic. Let's poke around at it for a moment. What word might this be? This is the secret word, and these are the rest of a bunch of words that exist in a, again, flattened vector space. But you can kind of see they run together, right? It's not perfectly flat. You can kind of see the hyperstructure beyond this. Looks a little bit like background radiation. Okay, let's go for cow. Cow's pretty far away. It's got a similarity rating of 5.7. How about banana? Well, banana's pretty close to cow in this particular projection. Okay. Train. Oh, okay, that's quite a bit closer. Okay. How about house? House is further away than train. Okay. Banjo. Oh, interesting. A little bit off, but whatever. But you see, the point of this game is you're navigating a semantic space. These words are closely connected to each other in different ways. Yeah, mess with that if you like. Okay, so let's recap. Sort of a primer and discussion on how the heck this stuff is possible. Recap. We are capable of discerning semantics from seemingly similar symbols, right? Cat and car have a lot in common, but they are very different things by the time they get into semantic space. And that makes sense, but how? So these semantics arrive from these symbols activating neural networks in your actual brain to give a more complete picture of the meaning behind the word, right? The symbol becomes meaning somehow. And it's often driven, at least in part, by co-occurrence, right? I see the same thing with the same thing every day. I will co-relate those things. They'll take on similar meanings. We can represent this kind of semantics in numerical ways, specifically vectors, right? Co-occurrence of words gives a basic sense of this. Yeah, okay. I wanted to talk about... Yeah, the angle between things is very key. Anyway, so more robust tools have obviously come than the basic one that we're showing with simple co-occurrence. But once we get the meanings of words into these numerical forms, they're ripe for computation, right? We can assess their similarity. We can digest them and make them more consumable by neural networks. I mean, it works for colors conceptually. It works for words, right? Colors are a mathematical abstraction of light, and those can take on meaning. Words are abstract shapes. Those can take on meaning. So current tech isn't exactly like humans do it, but it's also not off the mark entirely. Especially because you can just see this yourself when you interact with modern AI technology. It's pretty dang well at engaging semantically with the human users. If it couldn't do that, then we would have a different argument to make, but it just can. So here we are. Okay, and that's it. Thanks much. Talk soon.